Alright, how to calculus 12-0. I'm going to go through a curve sketching example that's a little bit different than some of the one that I did the other day. This one has a linear function and an exponential function multiplied together, so it gives it kind of a little bit of a different feel. Should be something that you probably don't feel amazingly comfortable with just free sketching right off the get-go. And that's good. So hopefully we can show that using some of the techniques that we talked about the other day, we can get a really good graph of this without having to understand a whole lot about it to begin with. So the first thing we're going to do is find the domain. So for this particular function, we have f of x is equal to x minus 3 times e to the x. So this is a combination or product of two separate functions that are a lot easier to understand. So we have a linear function x minus 3 and an exponential function e to the x. Both of these functions individually have a domain of all real numbers, which means when multiplied, the combination, which is our f of x function here, also has a domain of all real numbers. So I'll just write down that that's what the domain is. So that is our first piece of information here. That's important because when we go to do finding out our intervals of increase and decrease, as well as our intervals of concavity, we are going to be testing around zeros for the appropriate derivative, but we also have to test around anywhere where we have a discontinuity of some sort on our original function. According to what we just found with the domain, that doesn't happen. So everywhere is going to be defined, and hence, because of that, we're not going to have any, at least from since it's continuous, both of those pieces, and it has, it also has no domain problems. We're going to be in good shape for finding out stuff without it getting super complicated, even though it looks a little different than normal. All right, so next up, find intercepts. So for this particular one, we are just going to say that if I were to plug in a 0 for my x value, we're going to get a -3 e to the 0, which is just a 1, so we get -3. So 0 for my x gives me -3 for my y. So we found the y-intercept. The x-intercept would instead be when this expression is equal to 0. So let's think about that. So we have two things multiplied together. So it's already factored. Maybe not in the traditional factoring that you're used to, where it's like linear function times linear function or something like that. But this thing and this thing are both factors. So if either of them was to be a 0, then the entire statement would have a value of 0. So in this particular case, we have two options. We have either x minus 3 is equal to 0. That's pretty simple to solve for. So if x minus 3 is equal to 0, that means x is equal to 3. If instead e to the x was equal to 0, well, that would be the same thing as saying that the ln of e to the x is equal to 0, or sorry, ln 0. Which would mean x is equal to ln 0, and that actually is undefined. There are no values for 0 or negatives for a logarithm. So in this case, we would end up saying that there is actually no solution to this from that side of things. You may have just known that when you saw the e to the x equal to 0, and you have in your head that e to the x is one of these nice little functions like this, which stays above the x-axis. So being 0 is not an option. So we do find one solution to that, and that solution is at 3, 0. So another couple pieces of information that we found here, we have a y-intercept and an x-intercept. I suppose I could label those y-int and x-int, one of each. Great. And we have found this domain as well. And I've used that highlighter for something random, but that's fine. Next up, C. We are going to look at determining whether this thing has symmetry. So for us, what that means is determining whether it's even or odd or neither. So if something is even, it basically looks like this, which what that means is that it's a reflection of itself across the y-axis. If algebraically, that would mean that if you put in something of the opposite sign, it gives you the same value as the original function with the normal sign. If something, so that's even. If something is odd, just as a review, looks kind of like this instead. Whoa, except for it got a little bit too loopy there and didn't really look very symmetrical. So if something's odd, it's kind of like a double reflection. It would reflect across the y and the x-axis to go down over top of itself. Algebraically, what that means is if you put in something of the opposite value, it gives you something that is the same numerical value, or not size, same size, but opposite sign. So that would be what an odd function is. So what we're going to do is we just take our actual f function that we have in this question, which is x minus 3 e to the x, and we put a negative into it. So that's going to be negative x minus 3 e to the negative x, which really looks nothing like the original or the opposite sign of the original. So this is going to have what we call neither even nor odd symmetry. So we're not going to be able to abuse any symmetry in order to cut down on the amount of work that we have coming up, which that's pretty normal. It's too bad, but if you ever find symmetry, it's great, because then you only really have to test x values on one side of your y-axis, so positive values usually, and it tells you basically that all the negative, or the values that are on the negative side are going to be copies of the same sign or copies of the opposite sign, and you don't even have to run them through and figure out what they're going to be, which is really convenient. All right, so next up, find all asymptotes. So for this, we are going to use limits to properly show what's going on with asymptotes. Now, because we have a domain that's all real numbers, we actually do not have any vertical asymptotes, because vertical asymptotes become discontinuities. So it would show up as being a domain issue, and we found that the domain was all real numbers. So there are no vertical asymptotes, and so we don't have to kind of do any extra work to look for those. Horizontal asymptotes, though. Horizontal asymptotes are going to be defined as what happens to the function as you get really, really big values of x, or what happens to the function when you get really, really big negative values of x. So approaching positive infinity, approaching negative infinity. So the limit as we approach positive infinity of the original function is, probably could have just written down the original function, so x minus 3 e to the x. So the first part there gets really, really big when you put an infinity into that. So it's infinity minus 3. It's basically infinitely large. And then you have e to the infinity, which kind of makes the other infinity look small, if you believe that. But it doesn't really matter, because this is not an infinity times 0, where they're kind of fighting against each other. This is an infinity times an infinity. So it just gets big even faster than we could describe before. So this one is just approaching positive infinity, which means that there is no asymptote associated with that. As you go to the right, it basically just gets larger and larger and larger and larger, and it's going to do so actually at an increasing rate because of that e to the x. So nothing going on out that way. What about the other direction? So you might say, well, why are you testing this? Well, most of the time when you do a vertical asymptote, it's just the same number both sides. That's true for a lot of the functions that we've taken a look at, but this one in particular, actually, because it has an exponential function built into it, exponential functions, you probably, as we kind of talked about before, you know that they have very different behavior on the two sides. So one, you can kind of go up towards infinity, or maybe negative infinity, but on the other side, you have a nice asymptote that's going along. You might remember that from Pre-Cal A. So if I still kind of am assessing what's going on with this negative infinity thing, well, this is the same as negative infinity for the first bracket, but then you get e to the power of negative infinity, which is the same thing as e to the infinity in the denominator. Now, that actually sets up kind of like a L'Hopital's rule, but the problem is that it's not really looking like one. So I'm going to change this around a little bit. I'm going to tuck, prematurely you might say, that e to the x down into the denominator as an e to the minus x. So now the way that L'Hopital's rule is working, it's a negative infinity up top and it's positive infinity down bottom. So you get that infinity over infinity setup, which is L'Hopital's rule ready. And now I can say that the answer to this is the same as the answer to the limit as x approaches negative infinity of the derivative of the top, which is 1, over the derivative of the bottom, which is negative e to the negative x. So e to the negative x is e to the negative x times the derivative of the inside for the chain rule. The derivative of negative x kicks out a negative 1, so that's where that negative on the front came from. So now I have that this thing is approaching 1 over negative and then e to the negative x, which actually is going to be basically e to the positive infinity, which is infinitely large and positive, but you're getting 1 divided by basically negative infinity. It doesn't really matter whether it was positive or negative because 1 divided by something extremely large is approaching 0. So we do find that there is a horizontal asymptote, and that is at y is equal to 0, but it is only the left-hand side of the graph that's actually going to follow along that asymptote. The right-hand side is going to tend towards positive infinity. So, okay, great. We got another piece of information. It's a long process. We'll keep going. So find the intervals of increase or decrease. Now, I usually at this point say, hey, we get to use some calculus, but I just use L'Hopital's rule, so that's you got to use a little calculus before we get to the derivative parts. So in finding intervals of increase and decrease, I'm just going to write down my function again. I tend to do that a lot. You don't have to. Now, we're going to take this and figure out what its derivative is. So it's a product rule, so it's a pretty tidy one. So it's this thing left alone times the derivative of this thing, which derivative of e to the x is just itself. The first one's derivative is actually just 1, and then times e to the x left alone. So we would get, in this case, x minus 3. Actually, I'm going to expand that so I can collect. So x e to the x minus 3 e to the x plus e to the x, which gives us x e to the x minus 2 e to the x. And if I factor it back out, it's just going to be x minus 2 e to the x. Which is funny because it looks very, very similar to what we just had. It's just that the brackets dropped down by 1. So we had x minus 3 e to the x, and now we have x minus 2 e to the x. Now, that x minus 2 to e to the x, how are we going to use that to find our intervals of increase or decrease? Well, for this particular function, I'm going to number line it. And as I do that, what I'm doing is I'm actually going to be assessing the signs of the derivative at some special values. So the special values are any critical numbers that I found, which we didn't actually talk about that yet, but it's going to be what I used the last statement we found, what we use it for, and any domain issues, which we had none. So the question is, where is this equal to 0? So x minus 2 e to the x equal to 0. Well, this is a very similar question to what we asked earlier in the problem, because we were trying to find the x-intercepts, and so it was x minus 3 e to the x is equal to 0. And what we ended up saying was that e to the x can never equal 0, so it's only when x minus 2 is equal to 0, which means that x would be equal to 2. So this is what we call a critical number of this particular function, and it is the only critical number. So I only have to put a 2 on this graph, which, or on this number line, which means it's probably a little overkill for what it is, but I just need to test my derivative on the left-hand side of this critical number and on the right-hand side of this critical number. What that allows us to do is understand whether we're increasing or decreasing on either side of this. So if we get an increase to decrease, which I got to think about my left and my right here, increase to decrease, that would be a local max. And if we get a decrease to an increase, that would be a local min. If you get an increase to an increase or a decrease to a decrease, then we will not have either a local max or min. You'll have some sort of saddle point, which we'll kind of make note of, but it's not going to fit into this idea of local maxes or mins, and it will kind of do something where we just leave out one value for our interval. But we'll see whether that actually happens in this case. So this particular function is actually really easy to deal with because e to the x is always positive. So I can kind of ignore that part of it when I'm testing the sign of the derivative. So really, all I'm doing is I'm picking some value over here, which I'm going to pick a 0. I usually don't write that in, but that's what I'm doing. I'm picking a 0, and I'm going to pick a 3 over here. So if I pick a 0 and I put it into the little green highlighted thing that I have right here, e to the x is always positive, so it's just x minus 2. 0 minus 2 is negative, so it's a negative derivative on this interval. 3 minus 2 on the other part, which is a positive. So we have an interval of decrease, which is the first one, and we have an interval of increase, which is the second one. So f of x is decreasing, I usually just say dec, on x is an element from negative infinity to positive 2. And I don't include the boundary as being part of the increase to decrease. Because if you do that, it should be in both, and then you're saying it's both increasing and decreasing, which is a little bit wonky. So I just say it's an open interval, and so it goes from negative infinity to just 2. F of x is increasing on x is an element from 2 to positive infinity. So there's only 2 intervals. It's really simple. It's just a single value. Actually, a lot of the ones that you've probably worked on, if you've done any practice of this stuff, probably have been a lot nastier than this, even though this is a little bit of a different feel because the exponential and linear together. All right, so we've found that. Now f, well, I guess I didn't label that, did I? D, and then E. The work for that really starts up here. And so we've done that, found their intervals of increase and decrease. Now, we've actually already done all of the work for f, finding the absolute maximum and minimum values. If this thing had a defined domain, then or a closed domain, we would have to test the end condition, or the boundary conditions as well. We don't have to do that. It goes from negative infinity to positive infinity. So instead, all we have to do is say, at this value of 2, it's our only possible transition value. This thing goes from slopes that are negative to slopes that are positive. So this is a local minimum. Now, is this thing going to be an absolute minimum? Well, that depends a lot on how this function behaves. And out towards the ends, we have actually already shown when we were doing the horizontal asymptote work, wherever that is, right here, that this thing is approaching positive infinity on one end, so it's just going up and up and up and up and up, and it approaches 0 on the other end. So if we're saying that this is the lowest possible value, and you don't go infinitely downward at any point, that's actually true, that this is not just a local minimum, it's a local and it's the absolute. So it's going to be the lowest possible point on our entire function, and it's going to occur at 2 comma. It's really hard. It's not a hard thing to do, but it's a hard thing to remember when you're getting so into, I just use the derivative. Well, what's the derivative's value at 2? That's not actually what you care about. What you care about is this is a point on the original function that is important. So we want to put the 2 into the original function. So it's 2 minus 3 is negative 1, and then e to the x, so it's going to be e to the 2. So it's going to be 2 comma negative e squared is going to be the location of that particular thing. Now, anyway, I'm just going to leave it as negative e squared. It's an exact value that way. probably 7 point something or somewhere around there. I guess 27 squared. Yeah. Yeah, maybe 7.3. I don't know. Somewhere around there. Mumbling to myself now. All right, so next up, concavity. Concavity is going back to taking derivatives. Now, actually, I'm going to just do because we're going to do a second derivative, I'm going to, not that we need to because we've already found the answer, but I'm going to backtrack after we found that second derivative and show you that you could use second derivative test in order to figure out that we just had a local minimum instead of what we just did, which was first derivative test. So G, we know that the derivative, I can still barely see it up there on the top, is x minus 2 e to the x. So what we're looking for now is the second derivative, which is going to be, leave the first one alone, times the derivative of the second piece, because it's another product rule, plus the derivative of the first one, which is just 1, and the second piece left alone. So this is another one of those, just adding 1 e to the x onto this. So x minus 2 plus another e to the x is actually just x minus 1 e to the x. It's nice. Behaves really in a similar way for each of these. Now, what we're going to do down here is we're going to test concavity by seeing how the second derivative behaves on either side of any zeros that this would have. Now, the zeros are going to occur when either e to the x is equal to 0, which as we've discussed earlier, never happens, or x minus 1 is equal to 0, which just means we get x is equal to 1. So x being equal to 1 goes on to the graph as a place where we could change concavity because it has this 0 second derivative. And then we don't have any other values there because there's no domain issues where it does not exist. So I'm going to do this first, and then I'm going to go back and take a look at using second derivative tests. So in this particular example, again, don't usually write these down, but I'm going to just use 0 and a 2 as my test values. Just pick some reasonably nice numbers that are definitely on the correct intervals. So if I put 0 into the second derivative, my second derivative is right here. So that would be minus 1 times e to the 0, which is 1. So minus 1 times 1 gives me negative 1, but it's negative. The only thing that matters really is the sign. If I put in a 2, that's going to be 2 minus 1 is 1. E to the 2 is, again, e is always positive, or e to the anything. So that's going to be a positive on this interval. So it does switch. So if I wanted to state my intervals, I could say that the original function is concave down. I just say CD. On x is an element from negative infinity to positive 1. And then f of x is concave up. So concave down, the negative sign. Second derivative being negative means that you're shaped like this, as we talked about when we discussed that the other day. And positive second derivative means you're shaped like this instead. I usually do happy face, sad face. That's my lame way of talking about second derivative sign. So you'd have sad face, that's going to be negative second derivative. Happy face, positive second derivative. So in this case, our concave up goes with that positive, goes with that shape that I just showed you. And this is going to occur between 1 and infinity. All right, so we have our intervals of concavity, and we can talk about point of inflection in a second. But if I back up this train, now that we have this second derivative, and I say, well, what's another way to find out that this thing right here, the value of 2, which we said was a local minimum, how can we find that a different way? Well, actually, if we take that value of 2 and you see whether the second derivative is negative or positive there, which we already have from this number line down here, I already used 2 as a test value. But even if I hadn't, it would be over here somewhere to the right of this 1. And so it is positive on that interval. Positive concavity looks like this. If you know that this is a local max or min, and you know that it is positive concavity, then it has to be a min because it looks like a happy face, and then it's an extreme value on that happy face. If it was a sad face, then of course it's like this, and you have an extreme value on that sad face, which would mean it had to be a local maximum. So you can use second derivative test there too if you wish. It's really your prerogative, whatever you feel happiest using. And so we have our intervals of concavity, which was my G thing there, and we're getting there. Now we're going to do H, find points of inflection. So the point of inflection, it does switch between negative and positive. So there is a point of inflection, and it occurs at 1, comma, whatever 1 is in the original function. So the original function is x minus 3. So it's 1 minus 3 is negative 2, and then e to the 1, I believe. So I'm just going to put because it's e to the x. So just e. So negative 2e, point of inflection. So I'm just going to call it POI. Whoops. POI. That was really, really messy. Don't know why I'm going to take the time to rewrite that because it's going to be still messy because I'm not the neatest printer in the world. But all right. So point of inflection. Okay. So we are done. We have a lot of information and we're going to try to use it to graph things. So the reason why this is a good set of information is because we have a lot of points that are very important. We have a point of inflection, which means we change our concavity from sad to happy at that particular point. We also have the exact value for a local minimum. We also know that there's a horizontal asymptote. We also know that it has no symmetry. We know that it has an x-intercept and a y-intercept, and it has no domain issues. It's a lot of information. We try our best to piece it all together and make the best graph that we can. So if I start us off here and say, all right, let's take the asymptote of y is equal to 0, and I'm gonna do that even though I know it's really only out towards the, I think it's the left, if I remember correctly, where it follows along that. But there's an asymptote. I don't have a vertical asymptote. I do have a couple of nice intercepts, and I'm sorry for the spazzy scrolling up and down real fast, but I'm gonna have to do that for a little bit. So we have 0, negative 3 and 3, 0. So I'm gonna put both those down. I'm going to go 1.5 spacing. So I'm going to say that this is 0, negative 3. And I'm going to do the same thing for the x-axis. So I'm going to say that this is 3, 0. All right, so we have, and I know that it approaches up here, over there. There's no more x-intercepts, so it kind of just skims along and approaches 0 on this side. And I might need to kind of like move that around a little bit. It might be a little off in terms of where I put that. Although I usually, personally, I don't care a whole lot about how much the curvature is up there, as long as the curvature is the right type. So concave up, concave down. Which I might need to change that because it might kind of make it look like it needs to bend the other way. All right, so the only other points that I have are a single local minimum, and that local minimum occurs at 2, so it's like over here somewhere, but it's at 2, and then it's negative e squared, which I said was maybe around 7.3. I do remember saying that, but I don't have much confidence in that, so I am going to do a calc, and let's see. Oh gosh. So E times E equals 7.39. That's fine. All right, so what I'm going to do is say that this would be 7.39, so somewhere maybe, oops, of course it wasn't writing terms yet. 7.39, somewhere right around here. Now, I'm going to label this as 2, negative e squared because I'd like the exact value there if I can, so that's good. And then the only other one was what was going on for the point of inflection, which is negative 2 times e. So that's going to be close to negative 5.44 or something like that. So let's just take e times 2. So 5.44. And that was at, I guess my brain is, it's 1 comma, isn't it? Yeah, so 1 comma negative 5.44. So 5.44 would be kind of like here-ish. So this is at 1 comma negative 2e. Now, this thing is a point of inflection, the one that I just drew. So I need to make sure that that shows a switch between unhappy and happy. So when I'm curving this, I need to make sure that everything that goes, I'm probably going to start at this point. Everything that goes on this side is unhappy. So it's going to curve like this. Okay, and it should have gone through that, but it was a little off there. And then on the other side, I'm going to make sure that it's curving like a happy face because of that inflection point. So it's going to curve the other way. It's going to go down to a local minimum, and then it's going to go up like this. As you can see, if I want to continue curving up in a nice way, it's going to be nowhere near this. It's too steep of a growth. So I get a function that looks kind of like that. So this is my best sketch with all of the information that I have of the f of x function. And so that's that. Now, what I'm going to do is I'm going to take this and actually graph it. So in Desmos, so we can kind of do a comparison. I'm going to leave mine up. Let's see if I can hit the right one there. Yep. So this was x minus 3 times e to the x. Now, my scale, I don't know, it's pretty similar. I mean, it's a little bit different, but it's not big of a deal. It's not bad. So you can tell that I'm not the best at drawing nice curves. So this part right here is a little wonky, kind of wobbled there. It's not supposed to have a wobble. No changes in concavity there. But overall, it's not a bad graph. And so that's the type of thing that we're doing here. Hopefully that was helpful to do another example. I know they're really long, so I took a half an hour to go through that. I probably talk about it a little bit more than I would if I was just doing it on my own. I hope that you feel the same, and maybe you can move through that in a little bit of a faster way. But yep, that's that. And another example, and so hopefully that helps in terms of putting some of that stuff together for your next assignment. Take care, folks.